talk. Uh, have you started? Have you started? Yeah, okay. So we are now recording, Lou, so please go on. Thank you very much.
Okay, I'll start. So this is joint work with Scott Baldridge and William Rushwork and Ben McCarthy. I forgot to put that on this slide. I'm going to be talking about for quite a while in this talk, I'm going to be talking about the coloring background, some of which is also part of the joint work, but the initial part of what I'm talking about goes back to Roger Penrose and then to some work of mine prior to this project, which I think forms an interesting background to the project, as you'll see. And since the others are going to talk about the project as well, I figure I can take a little time and talk about the trivalent graph coloring. So that's what I'm going to do. And I want to remind you or tell you, depending on whether you're familiar with this problem, of a very beautiful problem about trivalent graphs, which is you want to color them on their edges with three colors. I could use various indicators for the three colors, maybe just 1, 2, 3. If the graph is in the plane, then you see there are two cyclic orders for the three colors that can appear at a vertex. Remember, 3 distinct colors at a vertex is the rule that I'm after. So it could be 1, 2, 3 in the clockwise order. It could be 2, 1, 3 in the clockwise order. And that takes care of all 6 permutations of 3 things, and so taking them cyclically. And we'll see why that's important, the cyclic order, in a moment. But here's an example of a little graph, sometimes called the ladybug, which has been colored. And here's an example of a graph which you can't color because there's no way to get 3, since there's only 2 edges coming into that vertex if there's a loop at a point. So what you don't want if you're going to try to color a graph is an isthmus. That is, you do not want an edge which, if you remove it, will disconnect the graph. So one says the graph is one connected, or one says it has no isthmus. Or one says it has an isthmus if you can disconnect it. So the theorem is the 3-colorability of isthmus-free plane trivalent graphs is equivalent to the 4-color theorem. That's its historical interest, this theorem, due to Peter Guthrie Tait. Same guy who made a lot of knot tables, as you know. Now, why is that? Let's look at that. You could be a little more colorful than 1, 2, 3, and we'll let our colors be R, B, and P, red, blue, and purple, in small letters for the edges. And then I'm going to think about coloring regions, as in the map coloring theorem, and I'm going to use capital W, capital R, capital B, and capital P for them. And I think of that set of colors as having the structure of the Klein foregroup, so-called, Z2, direct sum Z2. In other words, the square of each one of those colors is equal to the identity, and W, white, is the identity. And the product of any 2 of them is the third, and it's a commutative group. Now, if you think of that structure and start with a coloring of the map that you have produced by the 3-valent graph in the plane, and color some region white, and you have a coloring of the edges, then you multiply. White times blue is blue. Blue times purple is red. Red times red is white, and so on. And by so multiplying, you will find that you have colored the map once you have the edge coloring. And conversely, as you'll see in a moment, if you have an edge coloring, you can get a coloring of the map. So the basic relationship is that colors X and Y on either side of an edge connote X times Y along the edge. And of course, white will never appear, so you go from 4 to 3 in this process of recoloring. Now I'm going to use another construction, which amounts to looking at alternating circuits of colors in the graph. So, for example, look at this graph over here that's colored, the ladybug, and consider a red, purple, alternating circuit, which is going around like this. You can see my pointer, I hope.
Yeah.
Can you?
Yeah.
Do you see the arrow? You do.
Yeah.
Okay. So here is an alternating two-color circuit, red, purple, red, purple. But I want to think of purple as factored into red and blue, as it is in my group, right? Then this would consist in a red line, a red circuit, and some dotted blues that happened here. And it would look like this, you see? Here's blue. I have another circuit here, blue, purple, blue, purple, blue, and that's mostly blue and sometimes a bit of red. And so if I want to graphically indicate it, I use my dotted factorization, and I have a red circuit here and a blue circuit here, and those are two of the alternating circuits in the graph. The other type of alternating circuit is a, what am I missing? Is a red-blue circuit, which I have to indicate over here by simply walking red, blue, red, blue, red. But I bring to the forward two of the alternating types of circuits in the graph this way, and then I see something interesting, that the graph has now been drawn as an interaction of blue circuits and red circuits, where the blue circuits interact with red circuits by sharing a bit of edge, and then they can, in this one they only cross, but they can cross like this, sharing a bit and continuing on the other side of the edge, or bounce if they go along and then come back off on the same side. So those are the two types of interactions of the blue and red circuits that you can see. I see that I did not do the next thing I wanted to do, so let me actually illustrate this by making a drawing. So you see, I could draw some red circuits, some red Jordan curves, and they mustn't touch one another because red will not touch red, but red can touch blue. So I might have a few of these. And then I go and draw some blue ones. And they have to share an edge maybe, and they come back and bounce, and maybe they cross and eventually reconnect. And they must be disjoint from one another as well. And I can have fun making doodles of this kind. Like that. And I was hoping for a little nesting. Let's have a little nesting right in there. Yeah. Okay. Maybe another one out here. Well, you see, to your heart's content, you can go ahead and draw things like this, where, remember, the idea is that if you have curves of two different colors, they either share a bit of edge and cross each other, or they share a bit of edge and do not cross one another, like that. Now, what does this have to do with with anything? Well, among other things, it shows us how to get from the coloring of the edge coloring of something to, I guess I'm going to just draw on this. It shows us how, and it will show us in a moment, how to get from the edge coloring, which is what this is. This is an edge coloring of a certain graph. I don't feel like drawing the graph, but you can see it. Every time I made one of these interaction places, that's a vertex. Here's another vertex. Here's a vertex. Here's a vertex, 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 and so on. And this is an edge, and that's an edge. So I, in doing this doodle, have produced an underlying trivalent graph in the plane which is colored. It is colored by definition since I'm doing this doodle, and it makes it colored. And on the other hand, I convinced you on the other slide that any colored trivalent graph would in fact have this structure by looking at the alternating cycles in the graph of red and blue, red and purple, or blue and purple. So this structure is always present if you have a coloring. And so the four color theorem is actually saying that if you draw these doodles, you will get every possible planar trivalent graph without an isthmus. That's what it says. And that makes it feel a little more obvious, but it doesn't make its proof much easier as far as I can tell. But what I want to show you is that it does make obvious the fact that I can forecolor the underlying map, because I'm talking about coloring the edges, right? And what you do is the following. You say, all right, I'm going to start by alternately coloring in blue and, sorry, oh, I see, yes. I'm going to start by alternately coloring in blue and white, the configuration made by the blue circles. And let me give you an example of that off here on the side so you see what I mean. Here's a configuration of only blue circles. And I say, well, let's make the interior of that one blue. And then this whole outside, maybe it's surrounded by a circle, is colored blue. All right. And then this is colored white. So I'm two coloring the map, which consists of only the circles that are blue. And it alternately is blue, white, outside white. Now I can do that here. And that will make this region blue. And I'm just going to draw letters in here because otherwise it will become unintelligible. But there's a blue there, and there's a blue there. Now, out here in the region in between, oh, I'm sorry, I made a mistake. Easy, two. I wanted to make this little cycle in here blue. So, in fact, let me color that one in. All right. But now this whole thing here is white, so it doesn't get colored at all. But that means that outside of it, everything will be blue. And again, I regret my choices because it takes too long to draw something like that. So let's do it the other way. I hope I'm not confusing you. I want to make the outside region white. It will be permanently white. If it's white, then this region here will be blue. And I'll just shade it a little bit so you see that. Okay, that's going to be blue from that. Outside region white, this will be blue. Outside region white, and that's on this side and on this side of that. That makes this part, it's very easy to make mistakes. What mistake have I made? No, fine. All right. Outside region white, this part is blue. And in here, that little cycle contains white. And this will be blue as well, outside white to blue. You're forgetting the red. You just forget the red for a moment, and that's what you're going to see, right? So now we've done a two-color on the blue cycles, but now I think you see what I'm getting at, because now I'm going to do the same thing with red. So outside region white, that makes this part red. And remember, the red cycles don't know about the blue cycles. So this part became purple. It's an overlap of red and blue. That's going to be white. This part became red, and it's going to get an overlap of red and blue right there. And this part became red, and it's going to get an overlap in there. And now you see that you are staring at a four-colored map by the superposition of a two-coloring of the red configuration in white and red, and a two-coloring of the blue configuration in blue and white. And so that means that that a three-colored graph implies a four-colored map. And conversely, because we already checked the conversely. All right. So so that's the first part of what we need. That proves Tate's theorem, that the colorings in the four-color theorem are oh, there is one thing I forgot to tell you. Let's say it. One important thing, and that goes back to Kempe, who proved 5 colors and thought he had proved 4 colors, but in the course of what Kempe did, I forgot the 1860 blank, he pointed out the following. Suppose you had a map with excuse me. Suppose you had a map with many vertices at many edges at a vertex. Because after all, no one said it had to be trivalent if it was a map you were thinking about. And I've only talked about trivalent. So you might have somebody like this with quite a number of edges coming into a vertex. And Kempe said, yeah, but it will be sufficient to color this. Sorry. There it is. Oh, I made another one up there too, didn't I? All right. Good. He said the following. Take their vertex and erase it. And put a region in there. Like that. So you have a trivalent vertices coming in there. You just blew up this vertex into a lot of trivalent vertices and another region. Now suppose you could color this. Well, that implies that you can color this. Because coloring says that adjacent regions are colored differently. And if this was colored in such a way that adjacent regions are colored differently and you collapse it, it's still the case that adjacent regions are colored differently. You can have any number of colors you like incident to a vertex. You don't care. So, Kempe says that trivalent is enough. Okay. So now let's go back to where we were. And I want to say a couple more things about the structure of the colorings, the trivalent colorings. Note that every colored trivalent graph selects an even perfect matching. And one way of seeing this and seeing what I mean by perfect matching is concentrate on the purples. And take them as a set of edges. And then you see that you have grabbed all of the vertices in the graph because every vertex contains a purple. So if you have it trivalent, if you have it colored and you grab the purple edges, you have a complete set of edges, disjoint set of edges in the graph that grab all the vertices. That's a perfect matching. And so what you see is that finding a perfect matching is very close to finding the coloring that you're looking for. It isn't quite the same because the perfect matching that you have chosen is going to be even. And by even, I mean that if you were to remove the perfect matching edges, you will get a collection of cycles, in this case only one, but they will be even cycles. There will be an even number because after all, if you remove the perfect matching edges, if you remove the purples, then what's left is red and blue. And as you go around a cycle, you will alternate between red and blue and come back. Red, blue, and come back. So there must be an even number of reds and blues along any given cycle, and so it's an even cycle. So that means an even perfect matching. And so A graph is three-colorable if and only if it has an even perfect matching. Notice that this doesn't require planarity anymore. Planarity never was required once we got to three coloring the edges of a graph. You could have it out of the plane, and we'll come back to that. But of course, we're interested in the planar problem because the four-color theorem says that a one-connected trivalent graph in the plane will be colorable, and there are uncolorables off the plane. So what turns out to be easier than the four-color theorem is that every isthmus-free trivalent graph has a perfect matching. Won't necessarily be even. And now I get to Penrose's formula. I'll come back to perfect matchings. But this is Penrose's remarkable formula, which he proves, which he states in his remarkable paper on applications of negative dimensional tensors, published in '71. And Penrose's formula says the following: you wish to count the number of colorings of a planar graph, trivalent. Could have an isthmus. And the formula says your counting can be accomplished by this kind of skein expansion of the graph. You will take an edge and you will smooth it away, remove it by connecting without any crossover, and you will take the number of colorings of that minus the Penrose formula applied to the graph obtained by crossing these and again applying the formula recursively. We're not claiming that we're counting colorings after we start doing the formula. We're simply evaluating by skein relation. And the value of a loop is 3. And this will count the number of 3 colorings of the graph when it's in the plane. Now, I'm going to take the time to prove Penrose's formula and talk about why it works, and then about how different kinds of generalizations arise in relation to it. So first, let's just use it as a rule. Here is a theta graph, and according to Penrose, if I smooth it this way or I cross smooth it, I'm using, excuse me, I'm using a virtual crossing there for the crossover just to remind us that it isn't a vertex to the graph and it has nothing to do with anything except as a graphical device for our computing. Of course, if you had a non-planar graph and you tried to put it in the plane, you would also acquire some virtual crossings. Anyway, getting back to computing, here's 2 loops, and that counts 3 times 3, which is 9. And here's 1 loop, and that counts 3. Remember, it doesn't matter whether it crosses itself. It's still evaluated as 3. And we subtract, and we get 6. And 6 is the correct number of colorings for this theta graph. 3 for this edge, then 2 left over, and then 1 left over. On the other hand, here is the dumbbell, and the dumbbell has no coloring, and if you apply Penrose, you see it doesn't have any coloring by Penrose because you're getting the value of a loop minus the value of a loop, which is 0. And then some shortcuts, of course, are always available in these kind of calculi. For example, if you had a bubble, why then you apply the recursion to one of the edges in the bubble, and you see that you get 3 times no bubble minus 1 times no bubble, which is 2. So you multiply by a factor of 2 if there's a bubble. And then you can do other examples. For example, this example here, the ladybug is still 6. And then you find out that there's something interesting and strange going on here when you're not planar, which I will say more about. Here I've drawn an immersion of the theta graph. Yeah. Well, what I did was I have a different cyclic order here because this is going outward, and then it crosses inward virtually and connects here. But it's just the theta graph, and I go through the recursion, modify, pushing the graph around a little so you see a nice vertical edge to expand on. And you see that once I've expanded on this, that virtual crossing has made this one the single loop and that one the double loop, and I get 3 minus 3 squared, which is minus 6. Not 6, doesn't count correctly, but it fails even more spectacularly on some graphs. This is my favorite failure. here is K33. You can check that it's K33, the gas, electricity, water problem graph. The one where you have 3 points and 3 other points, and every point in one triple is connected to every point in the other triple. Anyway, a non-planar graph, and here is the forced crossing. At least one crossing ends up being forced like that. And you go ahead and expand it by Penrose's formula, pretending you could do that. And you get this and you get that. Now here, that little loop doesn't matter, and so this is the same as a box with 2 intervals on its sides. And here, the double crossing doesn't matter, and you get a box with 2 intervals top and bottom, but the difference between them is 0. They both are planar graphs, they're identical, and so their count is 0. So K33 gets 0 from Penrose's formula, but you can check that, in fact, it's 12. So what's going on here? I think I want to go back to my blackboard and talk about how Penrose's formula has its proof. So I want to give you a definition of Penrose's bracket. Penrose's bracket is equal to the sum. This is the theoretical definition out of which all properties will flow. The sum over sigma belonging to, K. He's a knot theorist. He thinks that everything is labeled K, but here we're doing graphs, and so it has to be labeled G. All right. The sigma belonging to the colorings of G, by which I mean colorings with 3 colors at a vertex. The product of over the C belonging to the vertices of G of what I'll call sigma of C. And sigma of C is going to be equal to plus or minus the square root of -1. And if we have the color in the form red, blue, purple, then it will be plus the square root of -1. And if we have the coloring in the form of blue, red, purple, the opposite cyclic order, then it will be minus the square root of -1. That defines sigma. So these are plus or minus square roots of -1. So we want to use this definition and show that this does what it should do. So the first thing is we need to show that bracket G will be equal to the number of colorings of G when G is embedded in the plane, when it's planar. So in other words, what am I claiming? So this will follow from the fact that the product of the vertex weights is equal to 1. It certainly will follow from that. That's what I must prove for you, that this product of plus and minus square roots of -1 is equal to 1. We need an example to see this happening, and then I will show you a proof. So let's suppose that we had RBP here, and there's a nice coloring of the theta graph. And what are the vertex weights? Well, this is an RBP, so it's a plus I, and here is a P is a BRP, so that's a minus I. And so for this coloring, sigma, we have that this product is equal to I times minus I, which is equal to 1. And if every one of these ends up being equal to 1, then we have the tautology that this is going to be equal to the number of colorings of the graph, right? So we need to check that this product is equal to 1. You should turn off your microphone, particularly if you find that things are a little boring and you're moaning or something like that. So let's look at this from the coloring point of view. From the coloring point of view, there are two kinds of things. Oh, whoops, I don't have to dotted line that. There are two kinds of things that will happen in our graph. One is this, and the other is this. And now let's write down the vertex weights here. Now this is a red, blue, purple, and it gets an I. And this is a red, blue, purple, and it also gets an I. On the other hand, at a bounce, you have a red, blue, purple, and that gets an I. But here you have a blue, purple, blue, red, purple, and it gets a minus I. So this gets a plus 1. And so in other words, bounces can be ignored. And this gets a minus 1, and it says that crossings should not be ignored. And furthermore, that it would have been just as good to have abbreviated the matter by saying there was a crossing here and it got a minus 1, and there was no crossing here and it got plus 1. It was ignored. And so we see that the product over vertices, did I write C? The product over the vertices of sigma of the vertex is in fact equal to 1 because the number of crossings is even. Done. Okay. When we have, it may be best illustrated with just some simple example here. Here I have one of those colorings. Like that, right? And from the point of view of the structure of crossing and not crossing, it has this structure. The red curve crosses this one twice. This red curve doesn't cross anybody. I can pull it back out. And this doesn't cross that one, but this one does cross this one and crosses back. So you have a collection of curves that are crossing one another transversely in the plane. The number of crossings is even by the Jordan curve theorem. So that implies that if G is planar, then Penrose's state sum is equal to the number of colorings. And we're done with that. Now, what about the remarkable expansion formula? Let's see what will happen to that. Well, now you want to concentrate on what a coloring will look like at one of these edges. And there are two cases, and then everything will become clear. Let's look at the two cases over here. Without loss of generality, I can assume that purple is in the middle. That's just the third color. And here I have a red and a blue. Maybe I have a red and a blue here. But the other possibility is there's the third color in the middle, and I have a red and a blue here, but I have a blue and a red there. And I didn't need this. Those are the two possibilities. modulo the fact that I could have any third color in the middle. But those are two basic possibilities. The possibilities are that these come not permuted or permuted. Think about that. What does it mean in terms of our graphics, and what does it mean in terms of the vertex weights? Well, let's just do the vertex weights. In terms of the vertex weights, this is a red, blue, purple, and it's a plus I. And this is a blue, red, purple, and it is a minus I. Right. And on the other hand, this is a red, blue, purple, and it's an I. And this is a red, blue, purple, and it's also an I. And of course, you realize what this is in terms of coloring. Let's draw it in terms of coloring, the two cases I just drew. We have red, purple, red, and we have blue, purple, blue. And in the other case, we have blue, purple, blue, and we have red, purple, and red. So indeed, this is the one which when you evaluate the state sum, it's going to be exactly the same as evaluating this state sum, and the coefficient is a 1. And this is the one where if you were to do this and you were evaluating the state sum, then you would get a -1, and it's a crossover between these two curves. And so you see the state sum breaks up into the sum of colors that have this form and the sum of colors that have this form. And every one of these contributes a -1 locally. So if you're going to write it as a sum of two disjoint evaluations, then you need to say that that the possibilities consist in this possibility and a -1 attached to this possibility. And of course, the value of a single loop is 3 because there are 3 colors involved. So this matter of how the vertex weights appear at an edge in the two cases tell you the whole story about the Penrose formula. And that's the proof of the Penrose formula. Now, there's something further that's interesting about this, and I want to talk about it for a few minutes. I think I will use some prepared material to talk about this, and then we will go back into the theme couple of themes that I'm working with. But let me use this other slideshow to tell you a little more about the way Penrose was thinking about it. The way I've told you is not quite the way he was thinking about it. Pardon me. All right. He was thinking about it in terms of abstract tensors, like these. Diagrams that could represent a bit of algebra if they wanted to. They have indices, upper indices, lower indices, and so are diagrams that could be thought of as tensors and used in graph theoretic situations or physical situations to represent tensors, depending on what you wanted to do. He had diagrams for everything. For example, for a metric, he might write a cup or a cap like that, and so on. And for the trivalent vertex, these are some quotes from his papers. You could see how it looked. Now you might have a delta, which would be equal to 1 if A is equal to B and 0 otherwise. And here is the prescription for the trivalent vertex. You see, epsilon ABC is the epsilon tensor, which when ABC is in the order 1, 2, 3 is 1. When it's in the other cyclic order 2, 1, 3, it's -1, and it's been multiplied by I. And he says attach a tensor to each vertex of the graph and contract them, and that's his formula. So it's the same as what I told you, but I didn't include any tensors in my formula. And then, of course, he derived a lot of formulas from his expansion, um, and some of them occur neatly without any minus signs in them, like expanding 4 nodes together. But alas, when you get to the 5-sided region, you get a nice expansion with a minus sign, and that minus sign is all the uncertainty in whether you can manage to prove that you could do away with 5-sided regions. So you still have the 4-color problem staring you in the face when you look in this formalism. But his idea, as you see, this is a quote from his paper. He says, here's the graph. You take 1 I epsilon ABC at each vertex, contract the tensor, and this will give you the number of colorings. That's his point of view. And then in this little slideshow, I'm repeating some things I already told you, so I won't go through that very quickly. I already told you these things. And about the perfect matchings. Here's a nice trivalent graph that isn't planar, the Peterson graph. It happens to be uncolorable. And what happens here is, here is a very obvious perfect matching for the Peterson, as you see. Alas, it's not even, right? There are 2 pentagonal cycles remaining. And now you can have fun trying to find an even perfect matching for the Peterson. It doesn't exist. And there are other ways to prove that Peterson doesn't work. So one way of thinking about this is to look for a perfect matching. And here's a nice example that I like. Now, sorry, I wanted to go slowly at this point. If you are trying to color a graph, you see there's a principle that came up in the course of what we were doing, and I think I better illustrate it on my slideshow so you see it clearly. It's important for what we're going to do. Suppose I wish to color this graph. Then we have seen in analyzing Penrose's argument that this formula works. We've actually seen that the colorings of this are equal to the colorings of this, where I think of colorings where these are colored, the red and the blue and the blue and the red and this was the blue. Colorings of this. Is there a question? I'm sorry. There's a question. Was there a question? No. Colorings of this where they're not equal. You see, you need a coloring like this, red-blue, where it's not equal. And then you can think of pressing them together and getting purple, like that. Plus, and the plus can be thought of as union, if you like, okay? Disjoint union. The colorings of the crossover guy, which in this case doesn't have any colorings. But again, not equal. So I have the following formula. The colorings of this is equal to the colorings of this, where this is not equal, plus the colorings of this, where this is not equal. And this is a tautology and allows you to find the colorings of the graph. And there's a plus sign there because I'm only counting colorings or looking at the union of the colorings, and I'm not worrying about any clever ways of counting. I have to look at each one of these and find out how it's colored. So let's look again at this from that point of view. Let's say I'm interested in the colorings of this. So then the colorings of this are equal to the colorings of this plus the colorings of this. And we recognize immediately, of course, that this is 0. Done. And as for this, yes, 3 possibilities here times 2 possibilities there, and we get 6. So we can think about the coloring problem by turning it into a bunch of coloring problems about associated graphs. Now, what does this mean? This means the following, that suppose I have a trivalent graph, and I want to find out about the colorings of this graph. Well, I can choose a perfect matching. Maybe this one, and this one, and this one, all right? I believe I just chose a perfect matching for this graph, yes? And then I could expand each one of them by taking the parallel expansion if I wanted to. Let's do that. Oop. Not equal, not equal, and not equal. All right, so then I have a collection of Jordan curves in the plane, and I have some of them connected to one another, and they say it's not equal to this one. And then I can ask, can I color that as it stands? If this was red, then red is touching both of these, and they're touching each other. There's no way to color that. But the four-color theorem says that if we replace some of these by this, some one of those replacements will solve, will be colorable. Someone, which one? And of course, by now you figured it out, that if you make this one into a crossover and that one into a crossover, let's do it. Let's be careful. I can't have something, right? But it does say that some one of these will work. The question is, which one? And I'm going to cheat. by, that's right. I better not cheat. Let's just look at it. I will cheat. So one way to cheat would be to just find a coloring and then take a look at which one of those cases is the one that works. So if we wanted to do that kind of cheating, we could start with white, and then this could be red, and this could be blue, and that could be blue, and this would be purple. In which case, I have a red here, and I have a blue here, and I have a purple there. So, and I have sorry, I'm taking up too much time with this. Purple, and red, and yeah, I'm definitely taking up too much time with this. I'm not going to go solving this one for you, but some replacement by switching will solve this. And so that's another way of thinking about the four-color theorem in that form, but also this way of expanding into these different graphs is a way of thinking about the four-color theorem that I want to come back to. And now let me go back to this slideshow and show you an example or two. Here, this is a nice example. This one here comes from a graph that I could have drawn but didn't. All right, you can draw the graph by putting in an edge here, an edge here, an edge there, an edge there, and an edge there, and so on. And you have a planar graph, and it's uncolorable, just like the example I was drawing. And you can ask yourself, under what circumstances will that thing become colorable? Some switching of those is going to turn it into something colorable. And in that case, I know the answer, so it's worthy showing you this. Let's look at this. So this is the one that I was looking at. And it's certainly not colorable as it stands, and you would like to make it colorable. And there are, how many different possibilities are there? There's two choices at every one of these, so there are 64 possibilities here, and only one of them works. Exactly one of them works. I'll draw it for you, and then you'll see that it works. I'm going to switch every single one. Now, you may not be yet convinced. I'd better trace a circle. I'm not intending to trace circles in the colors in the way I was doing. I am just simply trying to show you what one of the circles is here now, one of the circuits is. These are circuits that have to be colored differently from one another. Let's do one more. Now you see what I've drawn. I've drawn a Venn diagram, a three-circle Venn diagram, and it has three circles in it, and each one can be colored differently from the other two, and we're done. So this graph, the graph that was behind this, There's only one case where it ends up being colorable, and that's it. That's all it gets, and that's the situation with that guy. So so you can come very close to being uncolorable in the plane, even with very simple examples, but you never find yourself being uncolorable. I had some fun trying to turn this one into an uncolorable, and it successfully turns into an uncolorable but not planar by cross-connecting a few things. That's the situation here. This is the graph we were looking at. Okay, I won't go further in this direction. If you do go further in this direction, you realize that you can, if you want to, ask the following question. Now that we've built up this much work, you can ask, how to modify Penrose's formula to make it work for any trivalent graph, for any non-planar. And the answer, of course, is by now apparent from what we have already said. In a certain sense, it's by now apparent. Here is an example of a non-planar graph. And you understand, I'm just talking about it now a little bit without going into the detail. You understand that when we used the Penrose formula, we thought about all the different colorings of this and assigned vertex weights to them in such a way that the product of the vertex weights for each coloring was equal to 1. But what can happen is, in this case, is that you would have circuits that cross through one another and cross through one another with with the wrong number of crossings, not even anymore, because of the fact that there's a virtual crossing here. And so you'll have to handle the answer. The answer comes from handling the virtual crossings. You need to change the procedure of the Penrose formula to handle the virtual crossings, and then you can count the number of colorings of any graph whatsoever. That's one direction in which things go. I'm just telling you about directions, and then we'll go back to our theme. That's one direction in which things go. And I've told you enough so that you could go off and figure out what the solution should be for getting all colorings if you wanted to. The other thing is this, that if you have V, a vector in 3 space, and another vector then the formula for the vector cross product of these two is equal to epsilon in the kth coordinate of this is equal to epsilon ijk vi multiplied by vj summed on k. This is the correct formula. Remember, epsilon 1, 2, 3 equals 1, epsilon 2, 1, 3 equals minus 1, and epsilon with a repeat like that is equal to 0, the 3-index epsilon. That's the formula for the vector cross product, W, of course, here. So that what Penrose is doing is very closely related to the vector cross product of vectors in 3 space. And in fact, this leads to a vector cross product interpretation of the four-color theorem. The vector cross product interpretation is the following. Suppose you are given some product like A cross B cross C cross D. You have a bunch of variables, and then you say solve another association of them, because the vector cross product algebra is not associative. So we could try solving this, for example. Four-color theorem is equivalent to all such equations can be solved using only I, J, and K, the three directions in three space. We're talking about vector cross product algebra. Solved non-zero. Both sides non-zero. And you might wonder, well, what does that have to do with what we were doing? And I'm not going to go into the detail, but let me just show you what the translation is, and then you will see what you'll see that it fits into the framework that we're talking about. Let's say we use that one. All right, so I'm trying to solve A cross B crossed with C cross D equal to A cross B cross C cross D. And I'm going to tell you how you can do this by turning it into a graphical problem. You do the following. You think of A, B, C, and D, and you think of cross product as what we did at the vertex, because that is what we did at the vertex when we were thinking about that before. And then we take another cross product between these. There's another vertex, and so this is a tensor diagram in Penrose's sense for that cross product. And now we write the other one backwards. T, C, B, A. And then we connect these two together at the bottom and, of course, at the top. And this actually is the translation. If you wish to solve this, then you should color that. And if you color that, you'll find that everything works. Signs and everything work. And furthermore, a theorem of Hassler-Whitney implies that such tied trees suffice. So if you can show that you can color tied trees of this form, then you will approve the four-color theorem. And tied trees of this form become expressions like this in the vector cross product algebra. So those are some aspects of background that I wanted to mention to you. And now let's go back to what happens in the present project. So we're going along, and we've proved the Penrose formula. Here it is. We don't have to look at it again. But now comes another question that is very natural here, and that is, what about a Penrose polynomial? Why can't we take this gain relation of Penrose and turn it into a more general polynomial? Why not, for example, take the loop and make it into an arbitrary variable delta? Let's try that. Well, if you try it, then as we've seen, if you wish to evaluate such a thing, you can choose a perfect matching and expand on the edges of the perfect matching. And and you will get down to loops and evaluations of loops. And if you did it, for example, for this guy with this perfect matching choice, you will get that, delta minus 1 squared times delta. But if you chose this other perfect matching, you will find that you get a different result. And Scott Baldrige discovered this a while back and bit the bullet in the sense that he said, okay, right, that's true, but let's make it into a perfect matching polynomial. Instead of being a function of the graph below, let's think of it as a way of evaluating perfect matchings on graphs. And the fact that these turn out to be different means that these two perfect matchings cannot be moved one into the other. These are singularly different perfect matchings, and we have a graph polynomial that is measuring perfect matchings. Very sensible idea, right? Oh, and by the way, of course, if you take delta equal to 3, these will agree, of course, because we know that it didn't matter how I chose a perfect matching to expand the graph in order to get my result when I was doing Penrose. We saw that that is well defined at 3 for any choice of expansion. But if you start moving out into other variables, then you get perfect matching polynomials. All right. Now, I know you all know about virtual knot theory, so I'm not going to bother you except to remind you that we can think of virtual knot theory as virtual knot and link diagrams with Reidemeister moves and detour moves. Detour moves, being consecutive sequences of virtual crossings, can be lifted and replaced elsewhere. And this notion of detour moves is available for graphs, any graphs category where you have some virtual crossing. So we can talk about virtual trivalent graphs if we want to in the same breath. Reidemeister moves and detour moves. And now, let's generalize our perfect matching polynomial a little farther. Let's say that at a perfect matching edge, it will expand into the Penrose two types with variables a and b, multiplying them and a delta for the value of the loop. And this is the innovation that we introduce in our recent work. And it goes back actually for me to using the same idea on something related to the coloring evaluation, which I may mention in a few minutes. But let's stay with this one. We're going to associate to a graphical edge an ordinary crossing and a virtual crossing. So this will map the graph into a virtual knot diagram. And what will happen to our perfect matching polynomial when we do that? So let's watch. I see that in this show, I started explaining it in terms of its abstract operations, but we don't want to do that yet. I just want to see what happens. So here, you should be clear, and I introduced it too quickly, that I have two directions to go here. If I take a graphical edge, I'm going to associate to it this type crossing, and notice the type of crossing, and then a virtual crossing next to it. But if I were to multiply by the virtual crossing on the right, then that says that a graphical edge with a virtual crossing next to it is just associated to a knot theoretic crossing. So if I wish to go backwards, if I have a knot theoretic crossing and I go in the direction of the A smoothing, I put in the graphical edge. So I can go back and forth. So now, what does that mean in terms of our perfect matching polynomial? Well, here we are. Here is the crossing, and I'm going to replace the crossing by its corresponding bit of graph there. Now I'm going to expand this by the perfect matching polynomial, and then you'll see why we did this. Because you expand it, this way and that way. And you see that what happens is that you get a parallel smoothing and you get the other parallel smoothing. You get the two standard smoothings of the knot crossing, and the expansion lifted back over to the virtual knot situation is the bracket expansion. So what we see here is that the perfect matching polynomial on the graphs corresponds to the full three variable polynomial on the virtual knots. And if you have a virtual knot diagram and you wish to get a corresponding graph, you take each crossing and you replace it by the corresponding graphical edge and make a graph with a perfect matching in that way. So if you have a given graph, it may have many perfect matchings, and so it will go over to many diagrams of knots and links, and each one of them can be expanded by the bracket, and that bracket expansion will be the perfect matching polynomial for the graph. So by using this little functor here between virtual graph and virtual knots, we can translate things that are sensible from one category to the other. And the first one for us in this project was seeing that the perfect matching polynomial, which is certainly a good graph idea, is actually the bracket polynomial. So that's another graphical interpretation of the bracket polynomial other than the usual Tut polynomial way of thinking about it. And so we are exploring this domain. Now, in exploring this domain, we started at 9:30. So I'm past my time. Do I have your permission to talk for 10 more minutes? Anybody there?
Yes.
Will it be all right if I talk for 10 more minutes?
Yes, of course.
Oh, thank you. Okay. Okay, good. So getting back to virtual knot theory, one of the things that I'm doing here is the unoriented version of this. I didn't put any orientations on the links or on the graphs. And then it's most natural under those circumstances for these moves that you see on the graphs to be equivalences. And that means that at the virtual knot theory level, it's natural that you should have these kind of flips, which we've called Z equivalents in virtual knot theory. So I won't take you through all the reasoning why in the unoriented case I want this, but I do. And that's all right for evaluating bracket. If you want to pull back and forth other invariants that are not invariant under the Z move, then you need to take orientations more closely into account. But in my account of this here, I'm going to work in the Z equivalence version and the unoriented graph version. So we're going to assume that. We know that the bracket polynomial is invariant under this. The equivalence is you have a crossing flanked by virtual crossings. You're allowed to remove the virtual crossings like that. I won't talk about orientation. But then there is the matter of the Reidemeister moves. That's the first exercise. You say, well, what happens if I take something which I would cancel up to Reidemeister moves over here? Well, it turns into a little gadget like that. And then you see that the first Reidemeister move looks like this, the removal of a bubble which contains a perfect matching edge. And what about the second Reidemeister move? Well, it turns into something like this. So for example, this unlink here corresponds to this bit of graph here. And there's the third Reidemeister move, and it corresponds to this. And so you can track Reidemeister moves over in the graph category. Well, why would you bother? Well, of course, for the same reasons as in knot theory, because if if I take the graphs up to the Reidemeister moves, then I can write down some perfect matching polynomial that is an invariant of that. If I take b equal to a inverse and the d equal to minus a squared minus a to the minus 2, as we do in knot theory, then the perfect matching polynomial will be invariant under these moves. And so you get a version of knot theory happening over in the graph theory, which is quite interesting to think about. And Scott went further, working in the graph category a while back, and worked out Kauffman homology for these graphs. And I'm sure he'll mention that when he talks about it. And we are working on integral Kauffman homology for the graphs by thinking along these same lines. There are some very cute relationships that occur if you evaluate the bracket at I. And I think in the interest of time, I will not mention that, but I'm sure Scott will. You can tell by evaluating the bracket whether or not you have an even perfect matching. That's a nice correspondence between the issues that we have in the graph theory, when is it an even perfect matching, and the issues in the knot theory. So I want to give you an example or two, though, so you get a feel for this. So let's look at this example. Here's a good example. I have this virtual knot K and its mirror image K star, and I map them over to graphs. So in one case, I get this little graph here with a perfect matching and a crossover drawn. And in the other case, I map it over and I get a very similar graph, but you see the cyclic orders are different here. This arc goes on the outside. And you might wonder, well, maybe using the graphical moves, there would be a way to get from G to G prime. But of course, you know there isn't, because K and K star are distinguished between the knot and its mirror image by a bracket calculation. And that means that these two perfect matchings are distinct, even if you allow all those moves that I showed you that are the images of the Reidemeister moves. So there is a lot of interplay between possible moves in this graph category and the topology of the knots and lengths. Other examples are fun. Here is the trefoil knot, and I'm taking it as a 3-braided version. I mean a two-strand braid with 3 crossings. And I take it over here, and you get one of these little gadgets for each crossing. And take a look at the map, the graph that you got, and you will see that it's equivalent to K33. So K33 with a certain perfect matching corresponds to the trefoil knot. And the larger question of what is the entire class of knots that correspond to a given graph by way of all their perfect matchings is really an interesting question, and we don't know as much about it as we would like to know. Other examples, let's see. Here's a little theorem. Take a classical knot diagram, then the corresponding graph is an even perfect matching. And so if you take a classical knot diagram and perform the construction to get the graph, you get a 3-colorable graph, not always planar. So we're getting coloring theorems, not proving the 4-color theorem yet, but we're getting coloring theorems from the knot theory. Classical knots give you 3 colorables, some planar, some not. And the proof is easy, but I think I will just quote results now because we're near the end. Proof is easy by just thinking, oh, I can't dare not to show you this proof. You see, you want to remove the perfect matching edges. Blink, it's removed. But then you look at the remaining thing, and it's just the structure of the knot, and you can count the number of edges that you got and see that it's even. So it's not hard to check that you get an even perfect matching. Another result is that if you have any virtual knot diagram of one component, then you get a 3-colorable trivalent graph. But if it had more than one component, then you'll get you can get uncolorables. So those are some examples. As I said, one can think about coloring in general by this kind of association. and when you do that, you can use that to find perfect matchings that are even and so on. Those are all part and parcel of working away at this relationship. Another point that I wanted to make was that you can, if you want to, transfer the question of coloring the graphs over to questions about the knots if you transfer faithfully, and then try to understand the coloring problem in terms of the knot diagrams. But planarity gets complicated under those circumstances, and so this is something that needs to be thought about. There is an invariant of knots and links that is related to this kind of transfer, which is where I started in this subject a longer time ago, which is that if you think of coloring two things differently and restrict to two colorings, which is part of the three coloring problem, then you get a version of the bracket polynomial for virtual knots and links. That is quite an interesting invariant of virtual knots and links, which sums over colorings of the knot diagrams where if you smooth them, they have to have different colors where they're meeting. And this is very similar to the tautological expansion that I was telling you about before. So those are some of the things involved. And of course, the one that's looming larger with us is the fact that given a trivalent graph, we could define its covariant homology by taking K of it, and probably we want the stricter oriented version, and then taking the covariant homology of that, and then choose your covariant homology. We could use Vasily Manturov's version of covariant homology integrally and try to understand how that is working for the graphs. That's a present project. Or we could take William Rushworth's doubled covariant homology and work with that. And there's Tubinauer's version. So there are at the moment 3 versions of covariant homology for virtual knots, and all 3 of them should have some interesting relevance to questions about graphs and perfect matchings when we get this better articulated. So I'm going to stop at that point. Thank you. I can't hear you, Vasily. You must have your sound off. No sound coming through. There you go.
Well, thank you, Lou. Very interesting talk. Too long, but interesting.
Yes, I'm sorry. It ran over a bit.
Anyway, I gotta go now. So see you tomorrow.
Yes.
Hello? Vasily, we cannot hear you any.
Still can't hear you.
Yes, we can hear everyone but Vasily.
Yeah.
Well, Vasily, thank you for sponsoring this.
Yes. Thank you. So, I guess.
Oh, here, excuse
Here
me.
you are.
Actually, in the chat, there are some questions from Vasily.
Ah,
And
well, there's a lot of questions in the chat. Yes. Wow. I haven't been looking at the chat. Yes, of course, implicitly we are talking about categorification of three colorings. That's a nice question. What are higher dimensional analogs of perfect matchings? Can you use tensors to get three-manifold invariants? Well, all of quantum invariants are actually in the form of abstract tensors, right? Any quantum invariant of knots and links is written. Reshetikhin-Turayev method is actually tensorial. That's just a reformulation of it. And Vasily, you and I have done a certain amount of work with Kuperberg bracket. Oh, that's good. You're going to talk about categorification of three colorings next week.
That's the plan. So the last part of what you were talking about, just expanding that out.
Right. Oh, I'm sorry. That's Scott. Right. Good. Well, minor theory, the minor theory fact that I know is the theorem that any uncolorable trivalent has a Peterson minor, with no isthmus, has a Peterson minor. That's Tutt's conjecture, which is proved by Robertson, Seymour, Thomas. Yeah. Shouldn't the octonians come into this? Yeah. Or Clifford algebras, right? Thompson group, yeah. And sure, I will make the slides available. But that question about are tensors used in three-manifold invariants, remember, the answer really is that if you were to take the Witten-Reshetikhin-Turayev invariant of three-manifold, think of it as a certain sum of quantum invariants of knots and links. And then the quantum invariant of knots and links can certainly be expressed in the category in terms of cups and caps and crossings, and those become specific tensors. So many tensor expressions for those invariants. But on the other hand, to intensively actually look directly at the three-manifold invariants in that way hasn't been done by anybody, because, as far as I know, because it looks very complicated from that point of view. But that could be taking the wrong point of view. Maybe it's really important to think of them in terms of tensors. It's too bad we can't hear you, Vasily.
Can you check your microphone? Maybe that.
Well, anyway, I think we want to adjourn at this point, I'm sure.
Yeah.
And looking forward to Scott next week.
And I will upload this recording, the video recording, on our site, and with these questions, I think, from in the chat.
Are there other questions in the chat that you would like addressed?
No. I mean, questions from Mantrov Vashilovich, Mantrov. Yeah, I will collect them, and I will try to upload these questions with the video recording in our site.
Oh, good. Yeah. Mm-hmm.
Thank you very much.
If you could send me an email with location
link.
of the site.
Yeah. Okay.
Thank you.
Thank you very much.